keep going then. So thank you for attending the processing and analysing data session this morning. Our final speaker this morning is Lianl. Lianl is a PhD student within the e-research lab at the School of Information Technology and Electrical Engineering at the University of Queensland. She is funded through the China Scholarship Council, and she is currently 2 years into her PhD studies. The topic of her thesis is Semantic Annotation and Reasoning Surfaces for Sensor Data Streams. Today, Lianl will be talking about streamlining the analysis of accelerometry data to improve understanding of animal behaviour. Thank you, Lianl.
Thank you. Today I'm going to talk about the streamlining the analysis of accelerometry data to improve the understanding of animal behaviors. So I will talk about the challenges and the problems in the background. Then I will briefly talk about the system objectives, the architecture, and the software that we developed. Then I will talk about the evaluation, which includes the data collection and the evaluation metrics and the evaluation results. And at the end, I will talk about the summary and the future work. So we see the explosion in using animal-attached accelerometer devices to monitor animal movements and behavior. The main reason is because it's really cheap and affordable, and it's light, so not really affect the animal that much. So as a result, right now we collected a large volume raw trial accelerometer data stream, and they need to be analyzed. So how does the ecologist to analyze the accelerometer data streams right now? So step 1, collect the data. So usually they just catch the animals and put the accelerometer devices on animal and collect the data, and the data looks like this. Then step 2, they need to analyze the data. So what they do is they manually go through the CSV file, and then they say, okay, this piece of accelerometer data stream describes the running, and this piece of data is about the walking event, and this piece of data is about resting event. But they don't have the graph looks like this. So the step 3 is they try to visualize to understand what the animal is doing. So, for example, so how long does the animal spend on walking for the whole day time? The question is, why do we want to do that? Well, if we want to understand the animal health, the energy consumptions, or food or water requirements, then this is the useful information. Something we haven't done, but the ecologists are really interested in, is to combine the animal movement data streams with the animal tracking data stream to not only understand where they are, not only understand what they are doing, but also understand where they are. Right now we are facing some main challenges. So the first one is the limitation of the three-dimensional accelerometer data stream. Usually they are really numerical, unstructured, and complex, and in prices as they always in the poor data representation. Oops, sorry. So here I give you an example. This is a piece of CSV file data we got. So by this we understand this is the time information. But what about L7? So it is a temperature or its heart rate we don't understand. And we don't understand what's the measurement unit. So if this is the speed data, so the unit should be like kilometers per hour or it's meters per hour. And we also meet other problems like there's massive volumes of complex data there, but there are no common markups, which means it's really hard for the ecologists in different universities to share their data. So there is no common ontology for types of activity that the ecologists try to monitor. And also the next of automatic analysis tools. So the ecologists that we come across, they just manually go through the files and attach their description there. So it's really time consuming, and it's always expensive, and it also ends up with poor quality data. And the third main trend appears in the wild animal activity analysis area. because in this area, it's really difficult to monitor and analyze the data. So just imagine ecologists want to capture the cheetah's video. So you should know the cheetah can actually run 32 meters per second, but the fastest athlete we know, I know is that he can only run like 8 meters per second, so you know the difficulty in that area. So we decided to develop a system, and this is our objectives. So firstly, we develop a web-based repository to enable the ecologists to upload and share their data streams. And after they upload their data streams, and they can search and retrieve or reuse those data streams, then we need to provide annotation services. And these annotation services need to support the visualization user interface. The ecologists can visualize the accelerometry data stream and their corresponding video if they recorded the corresponding video, and they need to be synchronized with each other. And we need to also to develop annotation tagging system to enable the expert to attach their expert knowledge to segment data stream to describe the animal activities. And those annotations will be tagged by the predefined ontologies. So the third aim is to provide automated analysis services. So to build the activity recognition models. So this including the species specified classifier, which means for example, we use dogs activity to train the model. So we use this model to recognize the dogs data. But for the cross-species classifier, which means if right now we have the dogs activities, we use them to train the dogs classifier. But then we will use this model to identify the wild dingoes activities, because the wild dingoes data has nice ground truth data. And the third aim is to provide simple statistics visualization to help them to understand the activity recognition results. This is our system architecture. So for this system architecture, we have 4 components: the data collection components, and the tagging system, and the visualization, and the activity recognition component. For the data collection, the ecologists need to use accelerometry to attach on the different species and collect the data and upload the data to the tagging system. So after they upload their data to the tagging system, they can visualize their data in our visualization tool. So with this tagging system, the ecologist can, to attach an annotation to a segment data in the visualization tool. And then this annotation will be marked up with ontology and saved in an independent annotation server. Then later, other users can search and retrieve these annotations. So for the activity recognition part, so after we create a lot of annotations, so the ecologists can search and retrieve the specific annotation that they trust, and use them as the trained data set and train the classification model. So when the new data set comes, they can apply this classification model to the new data set and classify the animal activities and show them in the visualization user interface. So the statistic analyzer will take the classification result and input to calculate more information about each activity that the classifier has identified, like the maximum value and minimum period value. So in this study, we developed a semantic annotation and activity recognition system. We call it STAR. So this is the screenshot of the upload user interface. So by this user interface, you can upload your data and the corresponding videos, and this is uploaded data by other experts. And here is our visualization user interface. This is annotation user interface. So for this visualization user interface, it contains the plot visualization and video user interface. So this plot visualization is used to display the 3-dimensional X, Y, and Z accelerometer data stream. You can zoom in and zoom out, and they are synchronized with each other. So when you play the video, so you see this line here, so they will move as the video plays. So here the annotation user interface here is an example of our existing annotation. With this dialog, you can attach annotation to a segmented data stream to create the animal movement. So here we show an example of we try to build the classifier. So we search the existing annotation about low-level human annotations and use them as the training data set to train a classifier. So so when the new data comes, we apply this training classifier to this new data set. Then they will classify the activities and show the result here in the visualization user interface. So from the visualization user interface, you know that from here to here, that's walking event. And from here to here, that's running event. And here to here, that's standing event. This pie chart here that shows the statistic analysis result. So we know that this model actually identifies 6 activities that's including running, walking, sit-ups, lying, standing, and sitting. So from this pie chart, we know this person, his name is Jackie, he's one of our volunteer students. He actually spent 90.5% of his time doing the running activity. And so in order to evaluate our system, we use our D6A devices, which looks like this. It only looks like this big. So it's only like 7 grams in the air and like 2 grams in the water. So it's not really affect the animal. So what we do is we use this device to collect the data from 8 volunteer students and staff in the university, and we collect the data from 6 domestic dogs with different breeds and different height and weight. Then we collect the data from 3 badgers in UK. And then we use 4 standard evaluation metrics to evaluate our classifier accuracy. The performance of the classifier. So we use accuracy, precision, sensitivity, and specificity. So we did 4 experiments to evaluate our system. For each experiment, we create a high-level classifier and a low-level classifier. So high-level classifier is used to identify the animal's active and inactive events. It's simple, I know that, but it's really important because this is really important for the ecologists to know what the animal do, the activity events and inactivity events, and it's good information for their energy expenditure evaluation. And we also build the low-level classifier, which you use to identify more specific activities. So for the first experiment, what we did, we used humans annotation to create these 2 data model classification models, then apply them to the human data set to identify humans' activities, and this is the result. Then we did the second experiment, so we used the dogs annotation to create those 2 classifiers, then apply them to the dogs classifier, to dogs data, and identify the dogs activities. And this is the result. Then the third experiment is about the badgers. Then we create the 2 badgers classifier. Then we use this 2 classifier to identify the badgers activities, and this is the result. The fourth experiment is a little bit different. What this experiment tried to prove is that can we migrate the classifier across species? So we actually choose the well-trained dog because they can to do the same things as the badger, and their height and their size almost the same. Because they are well-trained, so they can do the same thing as the badger. So what we do is we attach the annotation to the well-trained dog's data set, and we get the annotation, and we train the 2 classifiers about the well-trained dog. Then we apply these 2 classifiers to identify the badger's high-level activity and the low-level activity, and this is the result. So from the result, we get the following conclusion is that high-level classifier performs better than the low-level classifiers, and the human classifiers performs better than dogs classifiers, and the dogs classifier performs better than badgers classifier. The reason is because the noise contains in the data streams. So when we ask humans to say, okay, do the walking, they can do perfect walking activity. And so that's why they contain less noises. But for the dogs, because dogs performs better than badgers, because, the dogs needed by the owners, so they can still do walking, and running, but because the badgers, they are in the wild, so they do, by themselves. So that's why they are more wild data there. And we also get this third conclusion is that the species-specified classification model performs better than migrating the classification models across species, but migration still yield reasonable result. I think the performance almost here, like around more than 80%, so it's quite reasonable. So summary, so in this study we developed a semantic adaptation and activity recognition system which delivers an easy-to-use web-based repository, a set of semantic tagging and visualization and activity recognition system. So what we want to do is, in future, is we want to integrate the animal activity data streams with the GPS data stream to not only understand what they are doing in a particular time, but also understand where they are in a particular time. We also want to apply the captive models of wild animals. So 2 weeks ago, Hamish and I went to the Australian Zoo. So here is we actually put the G6A device on the tiger spot back. They asked them to, do walking and jumping and biting, so they jump like really high to get the activity. Then we put, the device on the dingoes and the wombats and other animals. So we get a lot of data. So the third future work is we want to improve the model accuracy by evaluating different machine learning algorithms. So my research was funded by the Charter Scholarship Council, and we would like to thank our bidder from Swansea University. He provided us with the badgers data, and I would like to thank Dr. Hamish Craig, because he spent a lot of time to help me to organize the dog's owner and Australian Zoo. They work together to collect the data. And I would also thank Professor Craig Franklin, because he's been always very nice and helpful and provided me a lot of useful information about the animals' activities. And I also would like to thank my supervisor, Professor Jen Hunter, for her support and encouragement. And this is our information if you are interested in, and this is our website if you want to, have a look at the software. And thank you.
Thank you very much, Lianl. Does anyone have any questions for Lianl? Could you please come to the microphone and say your name and your affiliation?
Hello, I'm Jennifer Graham from the University of Auckland in New Zealand. I was just interested, you said that you used predefined ontologies, and I wondered what the source was for that, because it's the terms people use when they're entering data that leads to poor data quality at the end.
Yes. Because right now, for example, at the beginning of this study, we have because the dogs do the jumping event, then the interesting thing is some of our groups, they say, okay, this is a jump event, but others say that we should use the leap word. So what we do is we actually, to talk to the experts to know, for example, the dogs, what the activity they have, and what they prefer, the words they want to use to describe this word. So we use the semantic technology, that's ontology. So you have inactive, so that's the inactive and active classes. Then the subclass of the activity should have running, walking, jumping, like that. So that's our ontology to use to describe those. So eventually they can use this, when they create the annotation. So that means if I go back to here. So if here when you create an annotation, you need to choose, do you want a high level that's active and inactive, or you want low levels? If you want to active, when you put the jump here, they will suggest the word contains in the ontology to let you choose. So you want to use jump or something like that. So not just you input it by yourself. Usually they will suggest you just input one letter or something. They will suggest the word in the ontology. Yes.
Does anyone else have a question? I have one question. I'm Bernie Pope from VLSCI. You mentioned early on in the talk that you had to deal, or ecologists had to deal with large data sets, and I was just wondering what kind of size of data sets you might be talking about, and, for example, how long would you have an accelerometer connected to an animal in the wild?
Because this project is a case study of the OZ track project, so they actually put the GPS on the first image, the first presentation slide. They have put on the crocodiles on the head, so they all see. So for the whole year, that's the GPS data. Because for this study, we just do the experiment. So what we do is we put the device on human's body at the beginning. So we ask them to do 6 minutes walking or 3 minutes running, then 3 minutes standing. Then after that, we ask them to do randomly to do that. And then we also put this device on the crocodile in the Australian zoo, but we didn't use that data because the crocodile didn't move that much. So, but we actually put the devices there for 4 days. So because the device can get 1 per second of their data or 30 samples per second. So because this experiment, we don't collect that much data, but because this improves, they will try to put this device on the animals in for 15 days a month. Eventually, they will get a lot of data, like that. But there's somebody in the CSIRO, so they actually put the different accelerometer device on the call. So just let them go there. So when the by start, they did the cause migration, the GPS data to understand their migration as well as understand their activities there. So we only collect a little bit of data, but there are some folks that are interested in animal behavior. They collect a lot of data there. Yeah.